Chapter 12.5 is the normal curve. So thinking back to when we were creating histograms, certain histogram shapes are more common than other histogram shapes, and we're going to be going over a couple of the most common ones. And in all of these cases, the vertical scale is going to be frequency, as it usually is, and the horizontal scale is going to be the observed values. So the first one we're going to look at, the first distribution shape, is the uniform or rectangular distribution. In a uniform distribution, all of the observed values are going to occur with about the same frequency. That means all of the bars in the histogram are going to go up to about the same exact value. So it's called a rectangular distribution because it obviously looks like a rectangle. So that one's pretty simple. For a J-shaped distribution, in a J-shaped distribution, the frequency is either constantly increasing or constantly decreasing. So the one on the left here would be constantly increasing because it's going up from left to right. The one on the right would be constantly decreasing because it's falling down left to right. So we call these J-shaped distributions. And the next one is a bimodal distribution. And a bimodal distribution is one that where two non-adjacent values are going to occur more frequently than all of the other values in the data set. So typically this means that you're dealing with two distinct populations. So for example, we have this frequency histogram down here, and we can clearly see that we have this frequency, or that bar going up a lot higher than the other ones, as well as this bar over here. So bimodal, bi meaning two. So it's pretty easy to recognize a bimodal distribution for a frequency histogram. And the second last one, before we actually take a look at one of them more in depth, is a skewed distribution. A skewed distribution has more of a tail on one side compared to the other side. If the tail is on the left, the distribution is left skewed. If it's on the right, it's right skewed. So you can see down here we have this tail on this one on the left. That one's going to be skewed to the right because the tail is on the right. And the one over here has this tail on the left. So we say that that's skewed to the left. And as usual, the mode is going to be the class that has the largest frequency, which means it's the highest bar on the graph. So if we were taking a look at the ones above here that are actually frequency histograms, clearly this one and this one over here would be the mode because they go up the highest. But finding the median and the mean is a little bit more difficult. That tail on these skewed distributions is going to affect the mean. That's because every value in the data set is used in actually determining the mean. So the mean is going to be pulled in the direction of the tail. So these graphs down here refer to the frequency histograms right above them. Anytime we're dealing with histograms and they have these shapes to them, we kind of imagine this continuous curve over the top of it to help us determine some important values, which we'll see for the next distribution. So we can see that the mean over on the one on the left, the mean is pulled to the right because that one was skewed to the right. And then the one that was skewed to the left, the mean is pulled to the left. All right, now let's get into the main one, the one that the chapter is actually named after here, and that is the normal distribution. Another name for the normal distribution is the Gaussian distribution, just named after a mathematician. And this histogram here shows us what the normal distribution looks like. So we can see that it has the peak in the middle, and then it just slowly falls off to the left and to the right. So this is so important because many sets of data are just normally distributed or approximately normally distributed, and some examples of these are going to be something like heights, weights, intelligence quotients. Even GPAs can be normally distributed if there's enough students. And the way that we're going to be thinking about these from now on, the shape of this is going to be kind of how we did it in the previous one. We're going to imagine it with this continuous curve over the top of it. So if we take a look down here, we can see that it can look a little bit differently. It can be high and narrow, or it can be short and wide, but either way, it has to be bell-shaped. So the normal curve is also called the bell curve. And here are some properties of it. Like I've been saying, the graph of this distribution is called the normal curve. It is symmetric about the mean, and it's bell-shaped, and the mean, median, and mode all have the same value, and they're all at the center of the distribution. So if we take a look up here, if we were looking at this one with the histogram, this value right here in the middle would represent the mean, median, and the mode. Okay, so that's a very important property for this normal distribution. So hopefully some of this symmetry was pretty obvious with that normal distribution. 50% of the data is going to fall to the left of the mean, and 50% of the data is going to fall to the right of the mean. However, this isn't the only symmetry that we can have. So the empirical rule is going to give us a couple more types of symmetries with different percentages, and it's going to do that using the standard deviation of the data set. So the empirical rule says that about 68% of the data is within one standard deviation away from the mean. So what that means is that if we have this normal curve down here, and we have our mean, which is as usual right here in the middle, that means 68% of the data is going to be one standard deviation to the left of the mean, which is below the mean, and one standard deviation above the mean, which is to the right of the mean. So 68% of the data, of all of the data entries, are going to be one standard deviation to the left and one standard deviation to the right. And then the next thing is 95% of the data lies within two standard deviations of the mean. So for two standard deviations of the mean, that's going to be, using this graph again down here, that's going to be two standard deviations to the left as well as two standard deviations to the right. So 95% of the data is going to fall within those 2 points. And then lastly, 99.7% of the data is going to be within 3 standard deviations of the mean. That means we can go all the way to the left, 3 standard deviations away, and then all the way to the right, 3 standard deviations away, and 99.7% of all data in the data set is going to be between those values, which should make sense because if we take a look at it, this graph, we filled in pretty much all of the area underneath. So it should make sense that that's about 99.7%. And we could go, if we really, really wanted to, we could go to 4 standard deviations away, but we don't have to do that really because 99.7% of the data is already almost all of the data. So that's usually where we tend to stop. Let's take a look at an example. For a distribution that's normally distributed with a mean of 100 and a standard deviation of 10, determine the intervals. This should just say intervals right here. So determine the intervals for which about 68% of the data falls between. So we know 68% of the data, based on the empirical rule up here, falls within 1 standard deviation from the mean. So the way that we can actually set this up, if we want, using notation, is going to be, it's going to be x bar the mean minus 1 standard deviation and the mean plus 1 standard deviation. So x bar minus s and x bar plus s, that's going to be 100 minus 10, which is 90, and then 100 plus 10, which is 110. So what that means is that about 68% of the data falls between 90 and 110. And for B here, approximately, we want the interval for which approximately 95% of the data falls between. So that's going to be based on the empirical rule up here. That's going to be 2 standard deviations below and above the mean. So for this one, we can write it like this: x bar minus 2 times the standard deviation and x bar plus 2 times the standard deviation. That's going to be 100 minus 2 times 10, which is obviously 100 minus 20, so that gives us 80. Could have just subtracted 10 from the one that we just did up here also. For the next one, we have 100 plus 2 times the standard deviation. So 100 plus 20 gives us 120. And this means that about 95% of the data falls between 80 and 120. And let's take a look at the last one, 99.7%. So this is going to be 3 standard deviations away based on the empirical rule. So that's going to be the mean minus 3 standard deviations and the mean plus 3 standard deviations. So that's going to end up giving us the mean minus 3 times standard deviation, which is going to be 100 minus 30, so 70. And then we also get 100 plus 3 times the standard deviation, which gives us 130. So that means approximately 99.7% of the data falls between 70 and 130. Okay, so pretty simple for those ones. For this next example, we have that heights of females that are the same age are normally distributed. In a random sample of 500 females, determine the approximate number of females in the sample who are expected to have a height within 1 standard deviation of the mean. So by the empirical rule, approximately 68% of the data lies within 1 standard deviation of the mean. So that means 68% of the 500 is going to be about within 1 standard deviation. And in order to find 68% of a number, we're going to have to multiply the number by 68%, where the 68% is a decimal. So that's going to be 500 times 0.68. Remember, move the decimal 2 to the left. And we multiply that and we get 340 females. So about 340 females are going to fall within 1 standard deviation of the mean. And for the next question, we have how many are going to fall within 2 standard deviations of the mean. So we know that 95% of the data is within 2 standard deviations of the mean thanks to the empirical rule. So we're actually going to do the exact same thing as we did right above it. It's going to be 500 times 0.95. And that is going to give us 475 females. So about 475 females lie within 95%, or rather 2 standard deviations from the mean. For this next thing, now we're going to be doing z-scores. So z-scores are also called standard scores or standardized scores, and these are going to determine how far in terms of standard deviations a value is away from the mean of the whole distribution. So a z-score tells us how many standard deviations a data entry is away from the mean. And for example, if we have a z-score of 1.5, that means the data value is 1.5 standard deviations above the mean because it's a positive 1.5. And here's the formula that we're going to be using. It's going to be z equals the data value minus the mean over the standard deviation. And data values below the mean are going to have negative z-scores. Data values above the mean will have positive z-scores, and data values that are equal to the mean are going to have a z-score of 0. And the notation that we're going to be using is going to be z sub x, and that's going to be for a data value x. So whatever z-score we're finding for whatever data value, we just plug that in for x as a subscript. So let's go ahead and do some examples here. A normal distribution has a mean of 60 and a standard deviation of 15. We want to determine the z-scores for the following. For A, we want to determine the z-score for the data value of 75. So we can go ahead and we can say z of 75 is going to be the data value. Taking a look at the formula, it's the value of 75 minus the mean, which is 60, divided by the standard deviation, which is 15. So let's go ahead and calculate this. If you're plugging it in the calculator all at once, just make sure that there's parentheses around the numerator. Either way, we should get 15 divided by 15, which gives us a z-score of 1. That means that 75 is 1 standard deviation above the mean, which should make sense because 75 is exactly 15 more than 60. 15 is the standard deviation. Okay, and then for the next one, we want the z-score for a data entry of 81. So it's going to be the data value 81 minus the mean divided by the standard deviation. And we plug that in. And we end up getting 1.4. And that's going to mean that 81 is 1.4 standard deviations above the mean. And for 60, the z-score for a data entry of 60, that's going to be the data entry minus the mean divided by the standard deviation. So this is going to be 0 over 15. Anytime 0 is in the numerator, that gives us an answer of 0. And anytime we have a z-score of 0, that means the value is 0 standard deviations away from the mean, which means that the number is the mean, which it's pretty obvious if we take a look at the mean of 60, so clearly they're the same. And the last one here, we have 33, so a z-score of 33. Data entry minus the mean over standard deviation. We plug this in, and we get negative 1.8. And since it's negative, that means 33 is 1.8 standard deviations below the mean. So it's below the mean, less than the mean, because it's negative. So now we're going to be taking the concepts from earlier a little bit further. We're going to be determining the percents of data between any two values in the normal distribution. So we can do this for any normal distribution. Obviously, it has to be normally distributed as long as we have the mean and the standard deviation. And the way that we're going to do this is using the z-table. And what the z-table actually tells us, the one that we're going to be using, is it tells us the area underneath the normal curve. And it's going to be the cumulative area, which means it's the area that lies to the left of a specified z-score. Okay, and then we're also going to have to use the fact that the total area under any normal curve is equal to 1. And we'll see why we need that in a second. So this is what the z-table looks like. Anytime we have a negative z-score, so this is the z-table for negative z-scores, that means it's going to look something like it does over here on the left. The z-value is going to be to the left of 0. So for the standard normal distribution, I'm going to draw it out over here. This is just going to be a normal distribution, except the mean is going to be 0. That's because the x values down here, the observed values, actually are going to be the standard deviations z instead. So anytime we're thinking about these in terms of z, we can think about the normal distribution as the standard normal distribution. And we're going to have z values greater than 0. So we're going to have like 1, 2, and 3. 1, 2, 3. And then to the left, -1, -2, -3. So when we're using the z-table, that's kind of how we're going to be imagining our normal distribution. So let's get into actually what is represented here on this z-table. On the outside for our z-values, our z-scores are going to be right here and right here. So on the left part, we have the z-score to the nearest 10th. On the top row, we have it to the nearest 100th. So for example, if we were looking for the z-score of -2.96, -2.9 would be right here. 0.06 would be right here. Together, that makes -2.96. And where they meet, this value right here tells us the area under the standard normal curve to the left of that z-value. So if we have our curve here and we know the mean is 0 in the middle, -2.96 is maybe about right here, just somewhere to the left of it. And these are our z-values, so that was -2.96 on that horizontal axis. So that number, 0.0015, is the area to the left of that z-value underneath the normal curve. Okay, so our z-values are on the first column, first row, and then wherever it meets, all of these numbers here in the middle represent areas underneath the standard normal curve to the left of that z-score. So that was for negative values. For positive values, it's actually going to be the exact same thing. We have our z-scores on the first column, first row, and wherever they meet, it's going to be the area underneath the standard normal curve to the left of that z-score. And you can see here in this diagram, everything to the left is shaded in. So what you should expect from these is all of these values inside of here should be greater than 0.5, because everything greater than a z-score of 0 is going to have an area to the left of it greater than 50%, because 50% of the area is going to be shaded in. Everything with a negative z-score is going to have an area less than 0.5, because it's less than 50%, because less than 50% of the area is going to be filled in. Okay, so let's go ahead and do some examples here. And also, if we're trying to think about it in terms of a percent instead of an area, then in order to change from the area in decimal form to a percent, we just have to multiply by 100%, which means we have to move it 2 places to the right, the decimal place. Okay, let's do a couple examples. Let's determine the areas underneath the normal curve to the left of -1. So I always like to draw these out. You don't have to draw them out, but just to get an idea of what the answer is going to be before we actually do it. So 0, as usual, is going to be right here in the middle. -1 is just going to be 1 standard deviation to the left of 0, so somewhere over here. So if we want the area to the left, that's going to be this area right here. So without doing anything, we know this should be, I don't know, maybe around 30% or 0.3, definitely less than 50%, because less than 50% is shaded in. All we have to do, since we're looking for the area to the left, we have to find that value on the z-table. So let's go ahead and find the value on the z-table. So we're looking for -1. We know it's going to be using this table because it's negative. -1 is right down here. And it's -1.0. So that's going to be this first column. And that's going to be this value right here. The value where they meet. And that's 0.1587. So the area to the left is 0.1587 or 15.87%. So 15.87% of the data would fall to the left here, or 15.7% is shaded in. Let's take a look at the next one. We want the area to the left of z equals 1.19. So 0 in the middle, 1.9 to the right because it's positive. We want the area to the left. So that's going to be all of this area right here. So without doing anything, we know it's going to be greater than 0.5 because more than 50% is filled in. And since it's the area to the left, it's going to be the value on the table. So let's go find that value. So we're using the positive table, and 1.1 is right here, and then 0.09 is over there. So the value that they have in common is right over here, which is 0.883. So that's going to be the area to the left of z equals 1.19. Or we can think of it as a percent again, move the decimal 2 to the right, that would be 88.3%. Okay, now let's make these a little bit harder. We want the area to the right of 1.19. So we just did 1.19, we said it was right here. This time we want the area to the right of it though. So we just found the area to the left. The area to the right is going to equal 1 minus the area to the left. That's because the area to the left plus the area to the right has to add up to 1 because that's the total area underneath the curve. So the reason why we had to write it like this is because the table tells us the area to the left. So this is going to be 1 minus the area to the left. We just found out that that area was 0.883. So we're going to subtract those. And we're going to get 0.117. So that is the area to the right of 1.19. And for the next one here, even just a little bit harder, but these are going to be all of the different questions that we can be asked. We want the area between -1.62 and 2.57. So that means we want to find this area here. So -1.62 maybe about right here. Positive 2.57 maybe all the way up here. So we want the area between these. So we want this whole area right there. So the way that we find the areas between is we have to do the area to the left of the larger one, and then we have to subtract off this open gap here, which is the area to the left of the smaller one. So in this case, it's going to be the area to the left of 2.57 minus the area to the left of negative 1.62. Let's go ahead and find these on the graph, or on the table. So 2.57, here's 2.5, and here is 0.07, and it looks like they meet all the way over here at 0.9949. So that's going to be 0.9949 minus the area to the left of negative 1.62. So we go ahead and find that, and negative 1.6 is right here, and 0.02 is right here, and they meet right here at 0.0526. 0.0526. So what we do is we subtract these two numbers, and that's going to give us the area between, which is 0.9423. Okay, so a little bit more difficult for the last two. And now we're pretty much going to be doing the main questions for this whole chapter here. We're going to be finding the percent of data to the left, to the right, or between two data entries, except we're not going to be given the z-values, the z-scores, right away. We're going to have to find them. So first step here is going to be draw the normal curve, and then shade in the correct area that we're looking for. And then we have to use this z-score formula to find the z-scores of all of the data entries that we're using. And then we have to look at the table. And we have the three different questions when we are doing this. And we just covered all three of them. We're either looking for the area to the left, the area to the right, or the area between two values. If we're looking for the area to the left, it's just the value on the table. If we're doing the area to the right, it's going to be 1 minus the value on the table. And if we're looking for the area between two values, it's going to be area to the left of the larger one minus the area to the left of the smaller one. And then we're going to change the areas to percents by multiplying by 100 or moving the decimal 2 to the right. Let's do a couple examples here. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. We want to determine the percent of individuals with IQ scores, and the first one is below 115. So standard deviation and the mean. So let's go ahead and draw in the curve here. So this first one that I'm actually going to fill in is going to be the x values, which are the observation values. So we have a mean of 100 and a standard deviation of 15. I'm not going to bother filling all of those in. We're looking below 115. So 115 is right there, just somewhere to the right of 100. We're looking for everything to the left of it because it's below 115. So what this means is we have to find the z-score for 115 and then find the area to the left of that z-score and change it to a percent. So the z-score for 115 is going to be 115 minus the mean divided by the standard deviation. That's going to give us 15 over 15, which is 1. So what we could do here is we could draw out the standard normal curve, which let me just shrink this other curve. So what this means is that we are finding, thinking about it in terms of the z-table, we are finding the area to the left of positive 1 because that's what the z-score was. So we're going to be looking for the area to the left of 1 on the table. So this is now thinking in terms of z for this horizontal axis. And the area to the left of that, if you look at the table, is going to be 0.8413. That means the percentage of individuals with IQ scores lower than 115 as a percent is 84.13%. Okay, let's take a look at the next one for below 70. And if we're taking a look at it on the normal curve, that's going to be, this was a mean of 100. These are going to be the data entries. So 70 is going to be over here somewhere because it's below 100. And we're looking for the area to the left because it's below 70, so the left of 70. So first, let's go ahead and find the z-score. So the z-score is going to be z for 70. It's going to be 70 minus the mean of 100 over the standard deviation, which gives us -2. And something to keep in mind for these is when you're calculating the z-score, if you have to round, you have to round to the nearest hundredth. So now what we have to do is we have to look to the area to the left of -2. That would end up giving us 0.0228. And as a percentage, that would be 2.28%. So the percentage of people with an IQ below 70 would be 2.28%. And so a couple more. Let's do it for below 130. So taking a look on the normal distribution, mean of 100, 130 is over here somewhere. And below 130 is going to be everything to the left of 130. So let's find the z-score. So the z-score for 130 is 130 minus the mean divided by the standard deviation. That gives us +2, and I'm just going to round that to the nearest hundredth here. So we need the area to the left of that. Let me just draw out the table for it, the curve, just so we can verify that they're the same exact area. So this is going to be for z. So this will be 0. And then 2 will be over here. So the area to the left of 2 is going to be this area, which we can clearly see it's the same as the one that we just did on the left. And the area to the left of 2, if we look it up in the table, is 0.9772. As a percentage, that's 97.72%. So about 97.72% have an IQ below 130. And so a couple more here. We want the percentage that an IQ score is going to be, the percentage of IQ score is above 122.5. So let's go ahead and draw that out. So we have our mean of 100, and 122.5 is maybe somewhere over here to the right. We want everything above it, which means that's going to be area to the right. So we need to find the z-score. So z for 122.5 is going to be 122.5 minus the mean over the standard deviation. That's going to give us 1.5, which is 1.50 to the nearest hundredth. And we have to remember, since we're looking for the area to the right, it's 1 minus the area to the left. So we have to find the area to the left of 1.5. And if we look that up in the table, that's going to be 0.9332. So 1 minus that's going to be the area to the right of it, which is going to end up giving us 0.0668. And as a percentage, that's going to be 6.68%. So 6.68% have an IQ above 122.5. Okay, let me just real quick fill in the curve for the standard curve here. So you don't always have to fill out these curves and shade in the proper region in order to do them, but it's good to do it for the actual data values and for the Z values, because then you can verify that the area that you're shading in is exactly the same. Okay, let's do one more for this question, then we'll do just one other one. Let's do it between 70 and 115. So shading this in, we know it's going to be the area between 70 and 115. So that's going to be this area right here. So this time we have two of them. We have to find the z-score for each one. So let's do the z-score for 70. That's going to be 70 minus the mean over the standard deviation. That gives us -2. And then let's also do it for 115. That's 115 minus the mean divided by 15, which is going to give us +1. And let's go ahead and fill that in on the table, or on the curve rather. So that's going to be, for the z's, we have 0 here, 1 right here, -2 over here. Shade in the area between them, verify that it's the same area as the other one, which it is. So since we're looking for the area between, we need to do the area to the left of the larger one minus the area to the left of the smaller one. That's going to be the area to the left of 1 minus the area to the left of -2. Looking these up in the table, the area to the left of 1.00 is 0.9772. The area to the left of -2 is 0.8413. And we subtract these, and we end up getting 0.1359 is the area between them. Oops, I actually just looked at the wrong answer key. It's going to be 0.8413 was the area to the left of 1, and then the area to the left of -2 was 0.0228. There we go, that makes more sense. And now subtracting these, we end up getting 0.8185. Alright, that makes a lot more sense. So this answer as a percentage is 81.85%. So about 82% of the IQs are between 70 and 115. Alright, let's do one more question here. For example, assume that the length of time for a horseback ride at a trail is normally distributed with a mean of 3.2 hours and a standard deviation of 0.4 hours. And for the first question, we want to know what percentage of horseback rides last at least 3.2 hours. So at least 3.2 hours means essentially greater than or equal to 3.2. So this would represent an area to the right of 3.2. However, if you recognize that 3.2 is also the mean, then we actually have our answer without having to do anything. Since half of the data is going to be above the mean in a normal distribution, that means our answer is 50% last at least 3.2 hours. Okay, so you could have done this the way that we did it before, find the z-score, find the area to the left, and do 1 minus that to find the area to the right. You'd have found that we just end up getting 50%. Okay, let's do another one. What percent of horseback rides last less than 2.8 hours? So drawing this out, we have a mean of 3.2, and 2.8 is obviously going to be less than 3.2. And if we're looking for less than 2.8, that's going to be obviously to the left because it's less than. So we're looking for an area to the left. So first we have to find the z-score for 2.8. That's going to be 2.8 minus 3.2 divided by the standard deviation of 0.4, which ends up giving us a value of -1, so -1.00. And I'm just going to skip drawing the other curve for this one. So looking up the area to the left of z equals -1, that's going to be 0.1587 on the z table. So that means our answer as a percent is 15.87%. Okay, and the next one here, we want to know what percent of horseback rides last at least 3.7 hours. And filling this in, we have the mean is 3.2. 3.7 is going to be to the right. And at least, we have to remember, is greater than. So it's going to be greater than 3.7. So that's going to be an area to the right. Now finding this z-score for 3.7. That's going to be 3.7 minus the mean divided by the standard deviation. And that's going to give us 1.25. So we want the area to the right, which we know is 1 minus the area to the left. So it's going to be 1 minus the area to the left of 1.25. And that's going to be 1 minus, looking this up in the table, 0.8944. So 1 minus 0.8944 is going to be 0.1056. And as a percentage, that means 10.56% last at least 3.7 hours. And let's go ahead and take a look at one more, well, two more, I guess, one more of these kind though. What percent of horseback rides last between 2.8 and 4 hours? So putting this on the curve, we have our mean, and then 2.8 to the left, and 4.0 above. And we're looking for the area between those values. So we have to find the z-score for both of these. So z for 2.8 is going to be 2.8 minus the mean divided by the standard deviation, which gives us -1. And then we also have to find it for 4.0. So that's going to be 4 minus 3.2 divided by standard deviation of 0.4. That's going to give us +2. So finding the area between, we have to remember that that's going to be the area left of the larger one, which is 2, minus the area left of the smaller one, which was -1. And the area to the left of z equals 2 is 0.9772 minus the area to the left of z equals -1, 0.1587. Looking both of those up on the table. And we subtract these, and we should end up getting 0.8185. And as a percentage, that's 81.85% last between 2.8 and 4 hours. Okay, one more here. So in a random sample of 500 horse rides, so we determined in part C that 10.56% last at least 3.7 hours. So that means 10.7 or 10.56% of 500 is going to be our answer. So that's going to be 500 times 10.56% as a decimal, which is 0.1056, which ends up giving us about 52.8. Okay, and then just rounding that up a little bit to 53. Approximately 53 rides last at least 3.7 hours. Okay, so that is it for 12.5.